Here's quite the odd riddle. What color is gold? You might think the answer is obvious. Gold. But that's not necessarily true. On the nanoscale, at about 13 nanometers, gold particles actually appear red. Your mind is blown, right? Let's understand this difference in behavior between the macroscale gold metal and nanoscale gold metal particles. But first, what exactly is a metal? Sure, we know gold and silver are shiny and precious metals, but there's a lot more to metals than that. In fact, about 75% of all the elements are classified as metals. So what makes a metal so unique? Well, metals can be used as conductors of electricity, meaning they allow the flow of electric charges, such as electrons. Metals can clump together and have their electrons delocalized across all the positive nuclei to form a sea of electrons that allow such electrical flow. Metals are also malleable, which is just a fancy term that means that they can be hammered into different shapes. Now that we understand a little bit more about metals, let's look at how they interact with light. And for that, we need to start small. Really small, with electrons. Electrons are tiny negatively charged particles whizzing around the positively charged nucleus. And all of the metals around you have free electrons. Think of these free electrons around a solid, sort of like bees to their hive. Bees can go about wherever they please, but they never stray too far from the hive. These electrons are also organized into energy levels called orbitals. Just like how bees have a hierarchy starting with forager bees at the bottom and the queen bee at the top. There are only a few bees working near the hive. A lot of them are further out looking for food. Similarly, with more electrons, only some stay near the nucleus, and the others are organized further and further away into their orbitals. Just how the outermost bees interact with the environment, it is the interaction of the outer electrons with the light that give the metals their color. But what is light? Light can be described both as a particle, or a photon, and as a wave of energy. The absorption of light is how we see color. As sunlight hits objects, certain wavelengths of that light are absorbed by the object, and other wavelengths are reflected. These reflected light waves are what we see and are what gives objects color. For example, let's look at this plant. Why is it green? As sunlight hits the plant, green light is reflected, and the other colors are absorbed, which is why the plant looks green. Now back to gold. With all its electrons, gold in bulk will absorb blue and some green light and reflect red, orange, and yellow light, giving its gold color. If we go back to the bee analogy with light as a food source, the bees search through the food and only take back the ones they like and leave the ones they don't like in the environment. But why does this change as soon as we get to the nanoscale? Smaller nanoparticles absorb more light than they reflect or scatter, while larger particles scatter and reflect more light than they absorb. 100 nanometer gold particles look purple-blue because they absorb more red light, and 13 nanometer gold particles appear red because they absorb more green light. So let's go back to the riddle, what color is gold? Now you know that, well, it depends, and gold can be a gradient, including gold, purple-blue, or red. Gold's color changes as you go from the macroscale to the nanoscale, and what's interesting to note is that this change based on size is true for other properties as well, like toxicity, boiling point, and conductivity. Understanding these behavior changes can lead us to groundbreaking discoveries that can help improve the conditions of the world.